Good morning. We begin our lecture. Now it's the third one. I would like to show some algorithm to recall this algorithm. So I will share my screen. First of all, before we start the main topic of this lecture, I would like to show some ideas that we have discussed already. So it's prim algorithm here. In Wikipedia, we have detailed description, and I like animation here. So there is description. So it's very old algorithm. It was developed in 30. That's like 100 years ago, something. So it's a long, long time ago. What is the idea? You can look at the picture on the right side. It's some kind of demo. The idea is that we have a tree and we add step by step more and more edges. So we start with one edge and then we add edges. The algorithm of connecting is based on the distance from all not connected vertices, nodes, to the tree that we already have. So it's all. It is also always a connected component of the graph. Here, it's a spanning tree that will give us an estimation for our traveling salesman problem. When we have a branch and bound algorithm, we will need estimation, and the one of such estimations is spanning a tree. Okay, this one, and some kind of is a competitor, another algorithm. It's very old, maybe not so old, but 60 years or something, as you can see here. And I like animation here. So as you can see, there is a very simple code and the basic idea. As you, it is very easy to see that it's not connected component. So we have many edges, and then by somehow these edges are connected into one component. So the algorithm is just we look at the edges and find the shortest one, and we add it to our feature tree, and then another one, and so on. But we cannot add the edge if it creates a cycle. So as you can see, some edges are not connected here because they create a cycle there. The bonus of this algorithm, its benefit is that we can use it not for connected graph. So if we have like a social network, we know that social network is not connected component. There is a large social component, or giant component, like 80 or 90% of all nodes in this component, but not all of them. So it doesn't work for this component. But Kruskal algorithm is okay with this, so no problem. I would like also to share some news about this algorithm. So today we will talk about traveling salesman person problem. So it's TCP and branch and bound technique and methods. It is well known branch and bound algorithm. It is not a new one, but as you can see, it's Google. And the most cited well, articles, what 100 is rather old, so 95 or 93. But if we look at current year, so like 2021, so it's this year, so it's January. So it's just a month, and maybe some articles that have prepared before, but they are going to be published this year. So 1 month, and some other months. And we have many articles. So in algorithm, in applied sciences, and so on. A, a lot of many people, they still trying to improve this algorithm. So it's not something that is very ancient, like a Rome or like a pyramids. No, it's something always fresh, and people, they are trying to improve it and again. Uh, and this is the destiny of all problems, well, of most problems, which are known to be NP-hard problems. So when we know that there is no polynomial algorithm to solve it, we have to find heuristics to solve it. And for these problems, people, they have to improve and improve and improve, trying to find the best polynomial algorithm for this, or slightly polynomial, very fast. And I'm not sure that this will end. So yeah, people will try to improve a bit, maybe on 1% or half a percent. Okay, so it's fresh, and we know some algorithm, very old one. Today we also will have time to speak about a super modular function. This one. This expression for this. So supermodel, yeah, the I think this one better. If we have a function on sets, so like a set of ages, set of nodes, set of anything else that we can imagine in logistics. So there is f, it's maybe the shortest path, or it's time to solve the problem, and a is a set. So x is a node, and we if we know that a is included into B, so B is a very large set and A is smaller one, and then sometimes we can find the property of this sets such that if we have this function of set, smallest set, and we add this node and set, and this will increase this function larger than if we add this node to the larger one. So the increase will be smaller for the larger set. If it is true, and we can find problems where it is true, then we can say that it is submodular functions. Or similar, we can have a definition for a supermodular. It's just inverse one, but so they are very different in terms of complexity. So one of these cases is rather easy, and another one is very hard to solve. It's like a convex and not convex sets. Okay. I would like to tell a little about our previous lectures, about our main direction of research of our lectures. So our idea of this course is applied quantitative logistics. So we will try to focus on logistics, I mean routing and maybe assignment problem that we have already discussed. and we will try to stay focused on mathematics or computer science. So we don't want to use it like we usually do in management. So it's not just lectures of motivations. No, it is not. It's more about mathematics, computer science, more about computer science. And applied means that we will try to improve our algorithm to make it more fresh and more uh, applied for special problems. We will try to add here multi-agent problems and uncertainty and equilibriums and so on. There is a short list of algorithm. I don't think that we will discuss all of this algorithm, maybe not, but for us it's a great basis. We use it. We use this canonical algorithm like a prim algorithm or Pascal algorithm as a basic as a basis for our new models. We will use game theoretical ideas, uncertainties, maybe chaotic things, networks, and I think that we will have time to use Python to develop some software and some small project. I have told about several problems that we have. So about paradoxes, logistic paradoxes, about equilibriums, NP-hard problems, uncertainty, logic, motivation, and so on, epistemic logic, epistemic games, and so on. But it was the first lecture. The second one, sorry, was devoted to a prim algorithm and Kruskal algorithm and some other. I will just pass through it. Okay. Oh, I see that I can move it by mouse. Sorry. Okay, here. As I have told, we will use some parts from this course from the Netherlands. It's quantitative logistics. This professor, he conducted this course before, so he took very great ideas into this course. So that's great. For us, it's only the basis, so we don't want to restrict ourselves just by quantitative logistics, because we have applied logistics and we want to get into multi-agent things. We want to make it slightly fresh. But this is a very great basis to start with. And we have discussed a bit about what kind of problems we can solve in logistics in general, in optimization, what is combinatorial optimization. We were talking about graphs, what is it? Vertices, nodes, edges, and about some formal model of this. We have discussed what is K3, K5, K2, 3, and so on. We have discussed what partitions, closed, connected, components, and other terms that we will use. Some of them we have already used. Some of them maybe we will use. So forest, tree are very important. Spanning tree, we have discussed what is it. Spanning tree. We have discussed what is time complexity and memory complexity, because we maybe needed. We we have seen this table, so it is very good one to show how difficult complexity influences their time of for solving the problem. So as you can see, the very small numbers and then larger numbers and so on. So we would like to avoid factorial and even powers. So we would like to have like very small polynomials or logarithms there. So we have discussed assignment problem. Today we will touch this problem a little bit more. So the idea is that we have jobs or tasks, and we have workers, and we have a table, well, later, who can conduct which task. So we know times or just costs, and we want to create assignment workers to works that is optimal in terms of the minimal total costs. And we have discussed algorithm for this, Hungarian algorithm, for example. So we're talking about what is a regular graph, bipartite graph, what is the shortest spanning tree. Today we will touch this a little more. So the shortest spanning tree is just a tree such that every node in our graph is included in this tree, and at the same time the edges have this the minimal total costs. Yeah, there is definition, and there is greedy. I have told that it's not all the time that a greedy algorithm well constructed or just can be applied, and usually greedy algorithm cannot give us an optimal solution. For example, for traveling salesman problem, greedy algorithm is just heuristics. It's not optimal. But for creating a spanning tree, we have such a greedy algorithm. And we know that its complexity is not NP hard, so it's just n log n, as you can see here. So it's okay, because for 1 million, 1 billion, 1,000, for example, for 1,000, we have n thousand, okay, and logarithm of 1,000 is just about 3 or something, so it's a very small constant, so it's okay. Okay, there is a description of Prim algorithm and Pascal algorithm. Okay, we were talking about minimum weight or shortest path problem. We had an algorithm for this, the theorem, the proof. We had a Bellman-Ford shortest path algorithm here. We have discussed Dijkstra or wave algorithm to find shortest paths. It's very fast too. Okay. And we had discussed Hungarian algorithm for the assignment problem here, and we have discussed the specific example where we have for jobs and for machines, for cars, robots. We have solved it step by step, and we have discussed a traveling salesman problem. So we had a distance matrix, and we have cities, and we had to find a permutation. So it's an ordering on this set of cities. We want to visit every city only once, and we want to have the total sum of edges to be minimal. Okay, It's some kind related to job sequencing problem. That is very general one. And we have lower bound estimation for traveling salesman problem from this assignment problem. Here, there is a discussion and some experiments. Well, it's not very fresh experiments, and now when we are talking about 40 problems, it looks some kind of childish, because just 40 problems. What? Because now we have computers, we have mobile phones and clusters that are very powerful, and they can perform much more problems. But it was also very useful to just think about this problem, that, and these numbers, I think that they will be the same or very similar to larger number of problems. But sometimes it's not. So mathematically we can prove that it is so. It's just an experiment. Okay, and we just began to discuss branch and bound algorithm for traveling salesman problem or assignment problem. So there should be a simple branching rule, sub-cycle elimination algorithm with a simple branching rule, simple branching rules. We will discuss today in more details this idea, but I would just recall that there is a rejection rule there, breadth first algorithm, and there is an illustration how we can use it. We can use Hungarian algorithm here, and we have today we will discuss these pictures in more details. Okay, now I think this lecture. Okay, and now we are ready to start with our third lecture. We will consider, we will start with branching, branch and bounds algorithm. So let we have a subproblem pi, which involving n variables, in which some variable x can have one of four possible values, say a, b, c, or d. You can imagine any logistics problem. So it's not about necessary about traveling salesman person, routing, or assignment. You can imagine any problem you want to solve in logistics. Okay, we have imagined and variables, and we want to talk about one of them. And one possible, and we need a partition for this problem. So we want to split all possible solutions for this problem into several parts and compare them. So there, we need an algorithm, an idea for partitioning. Some of them are listed here. So the first one is the idea that if we have this problem, we set x equals a. So we just hold this value, and we try to solve this problem assuming that x equals a. Have another problem when we assume that x equals b, and so on, all variants. Okay, it's one partition. And when we solve all these problems, we can say that we solved the problem, the larger problem, because we know the solution for each of these problem, and we can compare them. And since we are trying to solve optimization problem, we are trying to find the minimal value of some function. So we just check which one, which solution has the minimal value of this function, and then choose. If we have several several variants that give us the same value of this function. We can choose any of it. Today, maybe we will discuss a little bit more this situation when we have several problems and the same value of optimization function, and we want to choose which one. But it's not our focus right now. Okay, first one. It looks like it is very difficult to imagine other variants, but indeed there are some of them. So the second one is just a binary tree. It generates a binary tree. So we say that x equals a or not equals a, and that's all. So we do not consider b, c, or d, and so on. So it's like a binary tree. Sometimes it's better, sometimes it is worse. It depends on the specific properties of the problem. And the third one, we can have another partition. So for x, so for example, the one branch is x a or b, and another branch is x equals c or d. It's also possible to consider this, but usually people they they choose the first and the second variant. Let's see the image. Last time, a week before, we have discussed these diagrams, but not in all details. We just discussed in general. So we have a large problem, and we have to split it, to divide it to several smaller problems, and there are three variants. So A, B, and C. The first one, the second one, and the third one. From these diagrams, it is very easy to see which one. Okay, when we have such a tree, we need algorithm to search and to solve this problem, to have an estimation for these problems. So we have several options. Of course, we can have some kind of combination of them, but usually people they want to distinguish two very large directions, two ideas. The first one is depth first search. It looks like we have one main variance, and we just trying to change very small pieces of it, more and more. You can see this tree. So it's a depth first tree. Here. So we have problem, and then we have another estimation, and so on. So we are trying to minimize this. So this is some kind of bound. So when we have not solved this problem, we think that the minimal solution is less than 23. Okay, but maybe we can do better. This variant 22 and this one 21. Okay, we understand that this one is more preferable than this one, and so on. And we come to the sub-problem, and we understand that the best one is 1. So this solution provides us with the minimal value of the optimization function. Okay, the breadth first is the opposite. So we have a tree, and we are trying to change every small changes there, and then we resolve several problems, but from the top and then. When do we need bounds? Okay, branching is very straightforward idea. Of course, we have to compare all problems, to consider all variants. That's okay. That's easy to see, and we can choose either depth first or breadth first tree. But bounds, we need if we don't want to solve problems or to consider some variants that we know that they're too bad. So we already know that estimation of this for the solution of this problem is very bad, and we don't need to consider all smaller variants of this solution, because we know that it's worse than we already found. So we have to focus only on the best solutions, and the bounds gives us some kind of algorithm of cutting off all bad variants. So we have branching functions here. The idea of branching function is it's like we are trying to assign to every problem the probability that it is the best one. So, for example, we think that if we have very long edges, then the probability that it's optimal is very small. It could be, but it's very small. If we don't have such edges, maybe the probability is higher, but still it's not 1 and it is not 0. So we can have such a branching function that will give us a priority of solving this problem. Here we can find a description of this idea. Okay, we will need some notation. So we have P for problem, okay, and we have opt from optimization, optimal. It's is the value of optimal solution to P. So it's the solution of this problem, indeed. And we are going to find such x that provide us x0, that the value of this function f is the minimum here. But sometimes when we want to know the bounds, we can use polynomial problems, for example, to solve it. I can illustrate it by the problem of trying to put several, well, no, about projects. I think it will be better, projects. Let's imagine that we have several projects or alternatives, and we have just a cost for this, and we have profit. Just we invest 10K and we get profit 20K, or we invest 5K and we get 100K. And let's we have the budget for this. It could be like 500K, half a million, and we want to distribute this budget among all projects. And there are several variants for this. The main thing, if we say that the cost is X, and we can describe the profit just like phi of X. So if we have X, we have phi of X, a profit for every project. So that we can index this. And for example, for 10K, we have nothing. If we invest less than 10K, the project is cannot be conducted. And when we have it, we have profit 20K here. And then, but it's not the only way of such phi. We can imagine that we can divide probably the project into several parts, or we can infinitely divide it. So we can say that if we invest here not 10K, but only 5K, but into the first project, we understand that 5K means 10K here. Sometimes it's true. For example, if you want to buy dollars, I don't know, or other resources. So here we can see it here. What is the difference? It looks like, why should we care about this divisible or infinitely divisible project? The first version, when functions phi looks like, the step function, isn't p hard. So in general case, we cannot in a polynomial time solve this problem. So if we have a resource and we have a list of projects, we have to spend a lot of time and comparing alternatives. So there is no way how we can solve it in polynomial time. But if we have infinitely dividable projects, then it's very easy. It's not even a polynomial, it's just a linear time. Why it is so? Well, it's very easy to see, and many students, they can see this. We just try to find the effectiveness. So we just divide profit by costs, and we have here 2, here we have 20, and so on. And we just spend all resource to the projects that have the best efficiency. And if we have spent all resource into the project, for example, this one, 5K, then we spend the rest resources to the project with the less efficiency, and so on, by priority. So it's like a linear time. Well, it's not linear because we have to sort it, but sorting is very fast. For example, it's like, as I remember, we have n log n or something. So it's very easy. So it's n log n plus n log n. And here we have NP hard problem. But we can try to use here branch and bound problem. Well, a branch and bound approach to solve this, because we can understand that if we have some solution, so we have budget R, and we can say that phi of R is the profit for us if we distribute this resource among all other projects, and then we can get the total of this project. And there is the first variance, like alpha for this one, and for this one we have for the same budget for the same project. And this one gives us a boundary for this one, because we cannot get for this problem solution better than we have here. So this one is always greater than this one. So we can have an estimation, and indeed it's a very good estimation, because maybe we shouldn't dive into details, but it's a good estimation. And we also can have estimation. We had upper bound for here, but this one is also very good, using only like a linear time, or linear multiplies log n time. So when we are trying to use branching and bounds, we have to solve in this picture here. So if we have no such approximation or bounds, we have to solve here an p-hat problem. We can we have to solve here an p-hat problem, and we have to do something more. So it's very difficult. But when we have a polynomial or linear, we can do it much better, much faster. Okay, and such estimation, we can say that it's x0. So if we want to have a relaxation, it's this process, as I have described here, is called a relaxation because we use some kind of infinitely divisible goods and so on. But okay, maybe I will tell more later about these details. And this x0 that provides the best estimation here could be not the same as the real one. So maybe this one gives us something very good, but our relaxation is not so good for this one, for optimal one. But it's just details. Okay, and we need the rule of branching. So we have to split our problems into smaller ones. For example, just the very straightforward way is like a clustering. So if we have traveling salesman person problem, and we have cities, for example, we have to visit this city or this city, or maybe in another order, and we have our customers in each city, several of them, and it looks like we have clusters here, the first one and so on. It's very straightforward way to split our problems, and p-hat problem TCP for these three cities into smaller ones. This one, and this one. It helps us to avoid such distances like going from this customer to customer in another city, and then back to that city, customer from that city, and back to that city. So we avoid it by clustering, and it's some kind of splitting. There are a lot, well, not maybe a lot, but there are several PhD that was motivated by this idea, and there are several research. They have special names for these clustering versions. They're rather fresh variants. They have some modifications. So it is a well-known problem. Maybe we will touch it, but later. So we maybe don't want now to focus on especially this variant of our traveling salesman problem. Okay, so we need branching, we need bounds, and we need lower bounding procedure here, relaxation, and some problem selection rule. So if we have three, we have to find in which order we should consider these problems. Sometimes it matters, sometimes it doesn't. Okay, some in some cases, it is very effective to use upper bounding procedure, because we know upper bound of this. But it depends on the problem, and sometimes we don't need this one. But in some canonical, well, in some in some modifications, uh, as I have described it before in the previous lectures, upper bounding procedure is very effective. And testing procedure, well, it's my uh, favorite one, testing procedure, because there is logical implications here. I have written several articles, scientific articles, academic, about these problems. But here we consider it as a part, and maybe we will come to this problem to discuss it in more details. The idea is that maybe we well, sometimes we can mm, without any estimation, approximation, and other techniques, just say that this variance is better than other variant, just by looking at this, and we can we can make a cutting off just by logical estimation. So we think, what if, then, so we have, and so on. But it's some kind of complicated. Maybe we will talk about this later. But it's my favorite one. Okay, and now we go further, and we want to solve to apply this very general rule for bound branch bound algorithm to a very specific problem, to our traveling salesman person problem. So we have several cases, asymmetric one and symmetric one. They're not the same. It looks like what kind of difference it could be. So asymmetric, symmetric, we just use algorithm and that's all. The problem is that the lower bound can be calculated in different variants, and symmetric means that we are not so free to well, in a symmetric variance, for example, we have such a solution, and that's okay. But in symmetric one, we have always more information, and we have to improve our bounds. I will show some details about this a bit later today, if we have enough time to discuss it. But asymmetric and symmetric does matter sometimes. Okay. They had some experiments of this, but we can not pay too much attention to these experiments, but because it's just only 100 problems. Maybe we should, in this course, try to make the same experiments, but for much larger number of problems. But I'm not sure. Maybe we should focus on logical and game theory problems. Okay. Yeah, and I have to say that as soon as we have exam and we have some tests and we also have project, very small project maybe for each of you, and you have to choose what kind of project, well, we can discuss it, you want to conduct, and then you will present at the end of the course. I think it's maybe fourth model. You will present some kind of presentation of this solved problem. Maybe, well, it will depend on you. So you maybe want to use some logistics in terms of projects, or maybe routing. Maybe you don't want, and okay, and we will discuss. So you have to choose during this course the topic of your project. but I don't think that you have enough information to choose this project, because I would like to discuss the basis and some ideas, or maybe it will take this lecture and the next one, and maybe the next one, and then we can discuss the possible topics of your projects, and it will be very interesting for you, because you will start to program, to make homework. Well, we will have homeworks. Right now, I don't think that it's very effective to use homeworks right now, but maybe next time I will prepare a homework task for you to solve. Okay. Now we just look at this content and trying to create a picture, the whole picture in your mind, that will help you to classify problems and understand what kind of problems we are going to solve and what kind of methods do we have. Okay. So there is a assignment problem. We use it as a lower bound, but sometimes this assignment problem gives us only a poor relaxation for symmetric TSP. There is a discussion about symmetric and asymmetric versions. Okay, and we can prove several expressions, but maybe not now. I will skip some details here, because you will have this text, and now you have this text. I mean, I have sent, I have uploaded it, this course into Telegram. Yeah, I did. So low bound here is optimal solution for spanning tree, and the length of age, and optimal solution for a traveling salesman person. So we are going to have this one, and this one yeah, not not better than lower bound, this one. And how can we get it? So we have to check the length of this edge, and we can check the shortest spanning tree. Here we can use Prim or Kruskal algorithm. For example, we can use for creating SST this algorithm, and we know the solution, so it's greedy algorithm, and it's very fast. This one is just a function, so it's fast. This is the fastest one. We can just take it. So we have very good, very fast algorithm to get a bound for our problem. Okay, there is some discussion how we can remove and node, and how we can get it. So the idea is that we will have example later. So maybe I don't need to draw a diagram right now. We will have it later. How can we get it for traveling salesman problem here? Okay, we need a unique cycle, which is Hamiltonian cycle. Hamiltonian means that we have a cycle, and we have every node in this cycle. So we don't have nodes that are not visited here. It's Hamiltonian one. And we can apply the algorithm that we have discussed. Well, we had not discussed it in all details, subcycle elimination algorithm, but here we can just have it as a given one, and do not, maybe to discuss it right now. Okay, so we have a cycle, some kind of cycle, and we want to improve it. So we can just take it what is the idea of branching? We can choose a node there with the maximum degree. What kind of degree? It's not Celsius, it's not Kelvin, of course. Degree of the node is the number of, well, for symmetric, just a number of rods from there. So for Moscow, for example, or St. Petersburg, or New York, London, they usually have the very great number of such roads and the maximum degree in this country, because all roads are trying to be constructed uh, to go to the capital, large city. So it's okay there. So, and we take one road and eliminate it there by deleting edges of the edge here and here, or maybe other edges. And this will give us problems. How can we get it? So we have some kind of restriction. So when we are trying to get a solution for this, like spanning tree and so on, we here just say that it is impossible to go through these edges. Okay, the problem is very old. I would like to emphasize that the basis of our course is based on the rather old problems. So it's classical solution. You can find details everywhere. I think in Wikipedia, as I did, and in articles, as I did, in books, and so on. There are maybe hundreds of books about this branching rule. But some part of our course will be very fresh, and I'm not sure that it is published anywhere already. But okay, so we split into problems, and then we have bounds and boundaries, and I have described before. Let us check the example. So we always want to have an example because we want to get this very abstract and difficult theorems. We want to have something that we can just look at very carefully and check details. It's like two example. Let us consider the matrix of distances between all pairs of 5 cities shown before. Here, well, there is no information here, but it's not. It doesn't mean that there is no information. It's just the symmetric one. So we have to put here the same numbers as there. So it's symmetric. So we don't need to use inks or pen to write it down. Okay. And there is a diagram for this. There is no first node, so we have to put here first node, and there is here roads to this node. This diagram becomes such that when we remove node 1, the first one, then we have such diagram. We can easily check it because we have, for example, 2 and 5. What is the distance? 2 and 5. We have 3. So this matrix is called matrix of distances, or, well, yeah, it's better to use. And we have here infinity. Well, we can say that there is 0 here because it doesn't cost anything to get from the city to the city back. But for some computational properties, usually, well, people sometimes use infinity instead of zeros. there are differences here. There could be differences. For example, if we have city A, we have city B, and there is one-way road, so we cannot get from A and be back in A. So there is no road here, and we have to move. Sometimes we cannot stay. There are rules that we do not allow don't allow us to stay at A. So we have to go from A, and we have to move somewhere, and then we have to go back. And we can sometimes if we have only one-way road. But it's just some details. Maybe we shouldn't pay much attention to this. Okay, when we have this graph, we can create a spanning tree. Look at this. We can use a prim algorithm or Kruskal algorithm. Later, we have a Kruskal algorithm. So we have we should find an edge with the shortest length. So is this one or this one? Okay, we can take this one. What else? We should try to add another shortest, this one, if there is no cycle. Okay, no cycle, it's okay. And we have to add another edge. Which one? 4, 5, 3, 3. This one or this one? From 2 to 3 is not allowed because we will have a cycle here. So the only allowed this one. We also can use a prim algorithm. How can we get it? So we take this one, this age or this age, and then check this. Well, I will rewrite it here. Sorry. Okay. 4, 5. Yeah, this one. Well, it's the same. And if it's a Kruskal. And for prim algorithm, what we should do? Well, we take this age, oh, another shortest age, and then we check by trying to find the shortest, well, the closest city to this set of cities. So if we want to get from 4 to this set, we have to spend 4 or 3. So 3. If we want to get from 2 from 5, we have to spend 3 or 2, 2. So this one is the shortest one, so we add it. And then we can add this one or this one. Well, we have only 4 because we should consider only cities that are not included in our spanning tree. So 4, and we should choose which one, which city should be connected with 4. 4, 5, 3. 3 is better. So this one is prim algorithm. As you can see, it's the same here and here, as we have proved before. Okay, now when we have a SST here, so I remind that it's shortest spanning tree, sorry, spanning tree. Here we can add 1. I can emphasize that we have solved the problem that is smaller, and we not even solve it. We used some kind of estimation for this. So it's some kind of solution, but we use is like a lower bound for this. For we can get it very fast. So Kruskal algorithm and prim algorithm very fast. But we need to solve the problem when we have all 5 cities. So we cannot exclude one and say, okay, we don't need it. We really need it. So we add it and we check. So the 2 shortest edges connected one to the rest of the graph are 1, 4 and 1, 5, like here. But it's not the solution here. We can say that, okay, we have a Hamiltonian graph and it's the solution, but it's not, because we can start with 1 and how should we move to get back? So we need cycle and Hamiltonian cycle. This one is not Hamiltonian cycle. And this is the problem when we try to have sub problems and we successfully solve it. How should we use this solution into the larger one? And there is the way. So we have the lower bound here, and we have lower bounds in the smaller problems. We can have, and we are trying to exclude several, well, not several, but exclude edges one by one to check these problems. So we exclude, as we can see, this one, and try to solve the SST problem here. It is easy to see that the solution will be 4, 5, 5, 2, 2, 3. This one. We had 2 here, and if we exclude, we have 3. And the cost is 11. So we have 6, 7, 8, 9, 12, 3 here, 3, 3, and 4, 11. But it's lower bound. It's a bound. It's not a solution. Here. Okay, then we can exclude another one from 4 to 5 here, and we have 1, 3, 1, 3. When we talk about 1, 3, it means that we 2, 3 is this one, binary tree. 1, 3 is just a cycle. And we have also 11 here, as we can check it. But this one is feasible too. Here. Now we can try to exclude this one. We also have a feasible tool here, and still, and we have 11. So it's a lower bound, and we have found a solution that exactly give us this lower bound. So we have found the solution. So we solved. I would like to show. So we took this problem. Wow. And we solved this problem using bound and branching algorithm. Branching and bound algorithm. Okay. Before we go to the stability and sensitivity analysis of these problems, I think we should make some kind of pause here. So we have a break. We will start from 10. Oh, maybe not 40, 50. Okay, we have 10 minutes before the break. So if you have questions, you can ask me. I will try to answer them, maybe right now or maybe later. You can write me or write to me at any time, or you can just send me a letter. It's okay to discuss some problems here. It's no problem because we have only not so many students here, so we can directly discuss some problems. It's okay. Okay, so before the break, we can discuss stability and sensitivity analysis of traveling cells of this problem, TSP. And sensitivity and stability means how can we change these costs or times and get the okay, I have conversation. Oh yeah, we can. Okay. Okay. Maybe I should wait a minute here and rewrite it. So we have yeah. So we have cities, 2, 3, 5, 4, and 1, and we have distances 2, 2, 5, 3, 4, 3, and we have distances from 1 and 2, distance 3, and we have 1 to 4, 1 to 5, 2, and 1 to 3. It's a planary graph, by the way. Well, but no, it's not a planary because you have a here problem. Okay, and from 1 to 3, you have 4. Okay, this is the problem. We have cities and we have distances, and the problem that we want to find a list of cities, like ordering, and to find the ordering for this. Okay, sorry. Maybe we want to visit first. Oh no. Okay. The city number 1, then the city number 4, then the city number 3, then 5, then 2, and back to 1. It doesn't matter which city is the beginning of our tour, because we visit every city, so we can start with every city, and the solution doesn't change. So this is our tour, but maybe it's not the best one. For this example, what we have from 1 to 4 is 1, from 4 to 3 is 5, from 3 to 5 have 2, from 5 to 2 we have 3, and from 2 to 1 we have 3. So we have here 10 and 14. This tour is not an optimal one. We know that the optimal thing is 11 here, because we have solved it. So this one is no solution, and we can describe this problem as P. This is our large problem, and we can have here such a division into several problems, smaller problem. Well, I even say that we should use not here, not here. So if 1 in our set of cities, or 1 is not in our set of cities, so we exclude our vertex here, 1. So if we have 5 cities here, for example, I can say 5. Here we have only 4 cities. But we also want to exclude some edges from there. So we have several options. And we have option 5.3. So it looks like we have P here. And we P1, it's where 5.3H is not part of our solution. We can try to solve the problem when we have excluded 5, 4, or sorry, yeah, 5, 4, and 5, 1. Why we do this? In our algorithm, we created, sorry, here. We have created a graph, and we are going to start by excluding edges of the node which has the largest number of edges. So degree here, like only 1. We have only 1 road from 2 to 3. Here we have 2. We have 2 roads here. We have 3. We have 2. And we have 2. So our favorite is 5. And we start from excluding edges from this node 5. And we tried to exclude 5, 3, 5, 4, and 5, 1. 3 variants, like I have written here. So it's edges of our vertex. Because we need a solution like a Hamiltonian cycle. So we need to have it like a cycle. But right now we don't have it. We have like this one. So we have a cycle here, but we have a tail. We don't need a tail, so we need a complete cycle. So we would like to exclude some edges from this point. It's 0.5, because there is 3 edges there. And we check, we exclude this one, the first variant, we exclude, and then we try to construct it. So we use the spanning tree with excluded this variant. It looks like we put infinity here. In this variant, we put, for example, when we exclude 5, 3, it means that here 5, sorry, this one. So we solve the same problem, but these 2 values becomes infinity. So we didn't allow this. Okay, so we checked and we tried to find a solution, and we found it looks like we had for our problem the solution here and here. We have 11 here and here. We are free to choose this one as solution, or this one. It's up to us. So we can this one and this one. But we have found the solution. And the idea The idea was that we have to exclude some ages. Okay. Yeah. Okay. Uh, is it clear how we do this? So if if it's not clear, we can discuss it later. Or right now, it's time for break. Maybe you will look at this more accurately during the break, or maybe later. You are free to spend your break for your purpose, not for just thinking about this problem. You can think it later after the break. It's okay. You will have time. Okay. Now the break, and we will meet. We will proceed. I'm not here. Okay. Okay. At 11:10. So I will meet you here in 20 minutes. Okay, it's 10 past 11 and we continue. So it was the example for the branching and bounding algorithm for traveling sales for TSP. Okay, it's a short variant for this. Okay. And then we will discuss stability and sensitivity analysis of this problem. It's some kind of natural, but well, we we are going to find some ideas, some approaches to have an optimal solution right here. And what if we change some costs? What if we change some times? What if we change something? Can we get the same solution in the same way? There is a very interesting, I think I can describe variant of the multi-agent systems when this idea is very fruitful. But it's still, I think it's not developed very good right now. So there are not enough investigations of this problem. Maybe it will be investigated during next several years, or maybe 10 years. Well, the idea is, let we have several person here. It's like a social thing, but we are talking about multi-agent idea, so it's okay. So why not? Or companies, for example, this one is, I don't know. No, okay, Coca-Cola. This one, Pepsi. I don't know, but another companies, or maybe it could be customers, whatever. And there is a solution. Well, there is a problem for logistics. I don't know, P1 here, P2, P3, P4. So there are managers there, and they work hard and they know optimal solution for these problems right now. And then there is a, well, and these solutions are different. So for example, in this solution for Coca-Cola, there is a road from A and then to city 2, and for Pepsi is from 2 to 3 is the first, for this one from first to 3, and here is the same for Coca-Cola. So you should visit the first city and then the second, this one. And then we have another company here, I don't know, X company, no name company, and we want to know what variant should we choose. We don't know. We have two options. We can solve, well, we have P5. We can solve our problem, but maybe it's not very easy. So if it's NP hard problem, then maybe it's very difficult to solve this problem. For example, we have a lot of cities there. I don't know, or customers, maybe not cities, but customers, a lot of them. And maybe we don't want to solve this. We want to use a solution, one of the best companies there, or not best, but competitors. We can use the solution from here, from Pepsi and from Cola, but they differ. And we know that the problem are not the same. So the problem are different and solution are different. So our problem is just, well, it can be like, this is problem in some metrics, I don't know, maybe it's a problem like a parameter there, and the solution. So we have Coca-Cola here, this problem, and there is a solution. And for Pepsi, so Pepsi has another parameter there, and it has another solution, and there is a solution for other companies. And we know the description of our problem, like here. What kind of solution should we check? Should we use? It looks very easy when we have only one variable here. But when our solution is just a graph or a very complicated structure, graph is okay. Then and solution is graph. So the problem is a graph and solution is a graph. Then there is no such space. Well, there is a space, but it's not so easy to draw, and there is special metrics of these and so on. So but we want to know which one should we choose. Maybe this parameter here doesn't matter at all. So maybe we shouldn't use x here that is less than x of Pepsi. Maybe this parameter is not very important, and the correct idea is just maybe here. So Coca-Cola is optimal, Pepsi is optimal, but there is no variance here because maybe it's not allowed by the law, but a local law, or maybe some, I don't know, other thing. So there are only two options. So here we have just to copy the solution of Pepsi, and that's all. But we have to check if our problem is close enough, because if we have a different, a very different condition, initial condition, we have to solve this problem by our own, even if it is a very large thing. So, and it's very similar to what customers do. So, for example, my friend, he bought a car, but he has his own needs. My needs is not the same needs as my friend's has. So this car is optimal for him. Is it optimal for me? I'm not sure. I can check internet, Google, and check all properties. It's very difficult. I can just copy the choice of my friend and buy the same car. But is his needs is very close to mine? I don't know. Maybe it's important. Maybe it is not. Maybe he lives in another town. Maybe in a different country, another country. So what matters, what is not. And when we're talking about a traveling sales person, we have graph. So what ages of this graph are important, and which one are not important? We can imagine that the longest ages are not important at all, because in any solution we wouldn't use them. Okay, but what about others? So how can we check the sensibility? So the area where we can use the optimal solution that we have, that we already have, and not to try to find it again. Another problem of this, well, it looks like a social problem. So we have many customers or competitors, but sometimes we can have to face this problem even if we are alone. For example, let's imagine that you are on the International Space Station, in Russian MKS, so International Space Station. There are some guys there, and they have a shuttle, or timetable, if you prefer British English. What they should do at every time moment. So this this guy should go to this device and conduct this experiment. This guy should have a rest, and so on. And you have some kind of shuttle. Sometimes it is very hard problem. Maybe it's not NP hard, but sometimes maybe it's NP hard problem, and they have a solution. Okay, that's great. You have it for 1 year. So, well, why we need it? Because there are restrictions on how much rest should be, how much time for eating, and so on. And there are some restrictions of how much time every person should use for each country, for Japan, for European Union, for United States, and so on. It depends on the budget. So if you invest some time, invest some money, so you have right to order. Well, you have some time for your experiments. Not all the time, but not entire time, but the small amount that is proportional to your budget that you have invested in International Space Station. So you have such a shuttle. Okay, that's nice. But what if something changes? So, for example, a guy he get cold, or maybe I don't know, he forgot about something, and you have two options. The first option is just to solve this problem again. So you have to solve these. Okay, maybe it's okay for International Space Station, but for railways, for aircrafts, maybe it's not a very good idea because you have to do it it's like in real time. But another option is just do not change anything. And how can we check? Should we or maybe we shouldn't? It's some kind of sensibility of tolerances of our solution. So maybe it's not important. So he has rest today or tomorrow. It doesn't matter so much. So we can use the optimal solution and just to rewrite several elements in our shuttles during these days, and that's all. We shouldn't rewrite everything. So this is the idea of this problem. There are a lot of modifications, but the main idea is some kind of tolerance, is robustness. There are different names for this. Okay, and here we have maximum decrease. Oh, sorry, maximum decrease and maximum increase of the length that are preserving the optimality of our solution. Yeah, I think I have described it in all details. Then there are some notation for this, and there is a theorem. It was proved assigned to this guy. I don't know him. It's like Libura or something. And he has proved that the tour is an optimal tour in graph. If we have well, be an optimal, yeah, tour here. If it is so, well, I don't think I should focus on this proof. I would like just to show that there is a theorem about this, and it was proved before. So there is a proof here. We can check two variants there, and there are obvious observation that this decrement doesn't change the optimality of this. Okay, but it's obvious, like it is stated here, that H tolerances are hard to compute because you have to compute equivalence and solve this problem again and again, and so on. Another problem is, as I have told, what if the solution is not unique? For example, you have a Hamiltonian cycle, like here, and you understand that this H is not allowed now. The first idea is just to say that everything should change, and we lose something because we have one problem. But maybe we have no such problem. Maybe there is another way with the same length. So this problem is the problem only for this cycle, but not for the uh, all of such cycles. Maybe there is another cycle with the same length, but without this age. And this is the problem, how to check it, because they can differ in all ages. Okay, there is an example. You can check it. It's just application of that theorem. There is another theorem about spanning shortest spanning tree. There is a condition. You can just look at this. It is very a short one. Okay, I will just go through this. There is an example, and I think we can look at this, but maybe we shouldn't discuss it. Well, I mean, if you have questions, you can ask me. It's okay, but it looks just you have to conduct all these steps, and you will have the result. So there is nothing very special about this. So there is a matrix of distances here. It's not the same as we had before. So we had another one. We can write it here. So, sorry. I have 1, 2. And here we have 1, 4, 4, 3, 4. 2, 1, 3, 3, 3, 2, 5, 1, 4, 5. Sorry. 3, 5. Not allowed. 5, 4, 2, 1, 5, 6, and 5, 2, 3. As you can see, it's not the same because we have from 1 to, well, we don't have an age with the length 2 from 1 to another city. So there's only length 1, 3, 5, and 6. And we want to check a tolerance. We will calculate the tolerances for all ages there in the solution. So the solution here, if we solve this problem, is here. It's very easy to see that because it is 1, it's a very short one, 1, 3, here, 3, 4, here, 4, 5, here. Yeah, it's a shortest spanning tree. So it's not the Hamiltonian cycle here. Then we have a theorem here. We apply expression, and we, as you can see, there is 5, 4, 5, 4. This is the same picture as there. But we check from 5 to 2 and from 3 to 2. Okay. And there is a table there. So the upper bound of tolerances here, we can just calculate it. You know. We can have a lower bounds for tolerances, just using that expression here. And we have estimations. Tolerances here means how bad can be, well, how can we change this length of these roads that the optimal solution will stay the same. Okay. But the traveling problem is not the only problem that we can solve in logistics. Sometimes we have to find the places for facility problem, as I have told. Wait a minute. Oh, we hadn't discussed. It's a Steiner problem. Maybe we didn't discuss it, but we can do it right now. So the problem of Steiner, it's the problem where should we place some additional points, maybe some additional points, but maybe we don't need them. So that this graph has two properties. The first one is that all nodes are connected, and the second one that the total sum of all distances is the smallest one. Why do we need such points? Well, let us imagine that we have this. It looks like maybe we need like a star here. And maybe these ones will be shorter. Then we want to connect all these points just without these edges. It depends, of course, on what are distances here. But I think that sometimes it can be, and the problem is that we don't know where and how many points we need. We can solve spanning, well, we can construct shortest spanning tree here for any variant with there is an algorithm here, and but we don't know how many points and where should we place there, and it's a very hard problem. And another problem is that if we have, it's like a facility location problem. For example, we know that we have a city and there are customers, and we want to have an offices there, like here, in such a way that we can split the city such that every office has his own area of responsibility. And the idea is how to make it. In what places should we put our offices? It's some kind of location. If we have government that want to, well, government, like, well, not government. For example, there is a store. Well, there are a lot of markets, a lot of supermarkets that are owned by a company, and this company want to optimize, and this company wants to find places for its supermarkets, like IKEA or Auchan, maybe, or maybe some other supermarkets, and they want, or stores, want to find the place in our graph. Okay, can we solve this problem? Can we formulate? Well, we can, because mathematics is a very powerful one. So we would like to formalize it. So there is a problem called facility location problem. Facility probably. We have set of clients, 1, 2, and so on, with given demand of a single commodity, and set of cities where facilities can be located. Okay, it's very clear. In the literature, it has been traditional to use phrase facility open to mean facility is actually established at site J. Okay, and let f of j be the given fixed cost of opening facility G, and assume there is a known profit Cig that is made by satisfying the demand of client I from facility G. If we have facility here, we have clients here, I don't know, I, and we can specify and so on. No. So the cost of this. Why do we need it? Maybe fuel, maybe time, maybe some other thing, and we want to find these places. Yeah, and there is typically is a cost file, a production cost at facility J, and it's well, it's a function of these two variables. There is transportation costs, yeah, and there is a special expression for here. So G is demand, how much fuel do we, how much product do our customers need here. And we have cost function, transportation costs, and so here. And we have price. So it's just economics. Maybe we shouldn't stop here right now, maybe later. So it's just an expression how we can get these costs from some economical ideas of the ground. Well, it is open a subset of facilities in order to maximize the total profit. So given that all demands have been satisfied. And you can see this here. So we want to minimize, I think minimize, maximize total profit to all instances. Loss of for any given is optimal to serve client is maximum over. That's profit is no, we need max profit. Don't remember, but yeah, we have matrix F. So what do we have here? We have matrix C is production costs. So there's costs, and F is wait a minute. Instance problems. I can't see where is F. Okay. It's the cost of opening facility. Okay, opening facility. Okay, and C. Oh, it's a profit. Sorry, it's a profit here. Profit here. Again, here profit. And we want to maximize it. Sorry, I was talking about costs here. That C is cost. I'm sorry, so it's not cost. It's just a profit. But we, of course, we can using costs calculate the profit, and using profit calculate costs. So using formula, special formula, and so on. But here we want to maximize it. It's our profit. So profit here, and we have some costs here. The one of the problems is how many such offices do we need? Because it's going to be very expensive to have a lot of offices there, but at the same time the profit may be greater. Okay, and we have the set of such so it's a subset of cities where we should place offices there. Well, it is very similar to bank account location problem. So there is a formalization there. It's also very ancient problem. Well, not ancient, but it's a very old one. So it's from the last century. It's 1974. So to formalize problem is it is written here, and we would like to find an optimal set of account locations. So now we are not looking to the for the roads or cycles. We are looking for the set. It's another target. So there is locations. We still have graphs, but we have now locations and potential set of account locations, maintaining course there, the volume of checks, and so on. So we have this problem here. Okay, and we can replace, but it's just some technical details here. Okay, we can check it. Another problem that is related. Well, why do we need to switch from the traveling salesman person to all these problems? Because we are going to use another algorithm. I think that we have enough time to mention it and start discussion. It's in our program. Also, it's the submodular and supermodularity of our functions. So there are special solutions. There are special algorithms and theorems for the special case of optimization problems, and such problems as clustering problem and other can be put into that domain of that problems that has property of supermodularity or submodularity. Yeah, well, if you have one property, you can switch to another property just if you put minus in your function, but there are some special features of that we will discuss a bit later. So that was the idea why we have switched from this algorithm to others. Of course, it doesn't mean that we have completely solved traveling salesman problem by that heuristics, or we have completely applied branch and bound solution. No, and we will discuss it maybe later, because there are symmetric, asymmetric cases, and so on. But now we are going just to check another domain and discuss it. And then maybe we go back to our training salesman person problem. Okay, so the idea here that we have we have many customers, just as it is told here, cluster representatives, classifications. It's very similar to Cummings problem, or maybe some machine learning problems, but we're not going to discuss machine learning problem here. I mean, in terms of neural networks and other techniques, we are going to stay in another domain, and we will try to use the theorems that have been proven for this domain. Machine learning, it's a good, well, neural networks and other algorithms, they're very powerful, and of course you can try it, maybe you should use in your everyday work. But now we are going to check that just what algorithm and what theorems can be applied here from the general mathematics, not the specific one of neural networks. So the clustering problem. So you have to divide your graph into several clusters, and you have special conditions on this, and you have profit, like we have discussed, and you have special special restriction on number of members in each cluster. It looks like we have a store with a limited capacity, or you have a bank account with limited capacity of money inside it. Oh, I don't know. There are many variants. It's like a supermarket with limited capacity of products and so on. But here we have a limit, a restriction on the just number of customers or members and clusters. So this cluster is for this store, this cluster is for this store, and you are limited by the maximum number of members there. And there is a special name for this. So as you can see, mathematicians, they like names, not only mathematicians. And there is a name, P median problem here. And there are many articles about this. Well, maybe not so many, sorry, but there are some articles. Okay, sorry. And we also can talk about assortment of structural steel beams. There are special problems when we need to find inventory and find what kind of products we need to construct. There is a description here. I think that it's not necessary to dive into details. Here we just check that there is a problem. It's more about like a survey or review of these problems. It's a very fast one. And we can see that this, from the computational point, this problem, assortment of structural steel, this problem is well solvable and can be reduced to the shortest path problem. And maybe you remember that we have Dijkstra algorithm for this that is very fast and so on. So we can construct a D-graph, and we have special correspondence there, and we can solve it. Okay, I will pass through. Okay, and what about complexity of that problem that we have discussed just before, just several minutes ago? So you have there is no, in general case, of course, no polynomial time algorithm for solving an NP problem, and that problem is polynomial is NP hard. There is such a solution, and like top of our discussion of such problems when we have switched is supermodular and submodular function. I have mentioned these functions at the very beginning of our lecture today, but right now we'll check what is it for our specific case, for our applied quantitative logistics. So we have a profit function, this one, and we have clustering like here, and so on. So it's just that problem that we have discussed before. So when we have several customers and we have to put offices there, and J is the subset of feasible points for these offices. It's very natural because when we see many customers, but we don't have enough building for our offices, so we don't want to construct a building. We want to just rent it, but not many buildings can be might be available for renting. So we have a special set of these. It's J here. So where we have a restriction here, and there is a profit. And this function has submodularity that we have discussed before from economical original idea. And the submodularity is here. I mean, if we use this one is submodular, and this one is super. What does it mean? How can we understand it and try to check what is it? Okay, this one is just a function there, and we understand that this one. So we have G, we have S here, so S, and we have several points. So we for every K is not of T, so T we have T, S, T, and we have J here. J. And for any K not in T, so like here, I think, here. And if we want to check the of this function of our this set and this point, and we want to check the difference, what was before we had this point and what we have now, and we check what if t here have if we add this point to this set. What is the idea of this? Okay, let K is the building here. So a company constructs a new building, and we want to check what about our solution, how much is better. And there are the first variant, if you have a larger set and we have a subset, and it's a submodular. If this increase in profit for our small set is larger than the same for the larger set. Well, how could it be? For example, we have a graph there, and this addition, this one node, is very important for our small thing, because we don't have, like, for example, we have here it's 1, 2, 3, maybe 5, and I don't know. Oh, okay, 5 here. And we can imagine that, sorry, this one is S, and okay, G and G, and so K Okay. This one without 2. This one is T. For any, not in T. No, a T is, okay, I just write it here. So S and 3 T 1 5 3 and J 1 5 2 3 and K is 2. And when we have such setting, and we want to check this function, or it can be, for example, it's the price of connectivity or clusters. The more clusters, the worst situation. So the best situation is when all sets are connected. Now we see that this set and this set are not connected here because this roads goes through the sec, the node 2, and it is not a part of the set S, so we can't get from 1 to 3 without going through 2, and 2 maybe it's something that is not allowed for those who not in G, so it's some kind of restrictions here. I can easily imagine the situation in a medieval age, but I think that now we can find something very similar, if it's country or if it is a trade union and so on. So we just can't get from 1 to 3. It's too expensive to go to find another way. So they are just separated here, 1 and 3. And when we want to find the benefit, if we add 2, so this one, like we'll count a number of clusters there. So add with a minus. So here we have -2 because we have 2 clusters here that are not connected. And if we add k, if we add 2, then we have -1. That's -1. And -1 minus -2 equals to 1. And here, if we have 1, 5, 3, and we add 2, well, it doesn't matter. So it's 1 here and 1 here. So it's just 0. So it means that if we define in such a way, we have that this function, that like numbers of clusters here, it is submodular. And we can imagine the situation when it is supermodular. For example, when many components is better than the situation when we have only one component. But this one is supermodular. As it is described here, yeah, and this is important because we have very good connection to that problem that I have described before. So as you can see, we have we can have a supermodel and go to the submodular just using minus, but properties will be will change. Well, I mean, not properties, but the problem of if we have function submodular and the problem if we have the supermodular are different. So complexity is not the same. Okay, and it was found many times ago, so it's about 60 or something. It's a very old problem. And the very important, well, here, is that profit function that we have written for those for that problems for those problems, I mean, bank accounts or offices and so on and so forth, it's submodular. It can be proven, so there is a proof here, but it gives a sense to all our moves here. So we had problems, we had special functions there, and we have a theory for submodular functions. Where is the bridge from them, from one to another? And there is the bridge. So the profit function is submodular. It means that we can use method and algorithm and theorem that we have for submodular functions. Okay, there is a proof. It's just inequalities. I think we shouldn't focus on this. We have a special exclusion principle for modular function. As you can see, there is a submodular, and for supermodular, we also have something. There is interval notation and so on. So I think that we skip at this time all the details. Maybe later we can go back. Sorry. Yeah. And if f, this cost, is a supermodular function, then this assertion holds. If we define this delta by this expression. I think we should pass right now, because if you focus on this, we can lose the whole picture. But later, when we have a whole picture, we can go back to this place if we need to, and then discuss in details all these things. So there is a proof here. As you can see, the proof is not very complicated. You should be very intelligent to check it. It's okay. But maybe, but I believe that you are. So there is a special submodular if f is a supermodular function defined on the interval, then we have several rules there for this. Okay. What about these rules? It was found. It was found by Chiroman long time ago, and it was published in the Goring, Netherlands, a long time ago, and in several other articles. Okay, and we can find, well, for this supermodular function f, we can use for solution a preliminary preservation algorithm here. And there is a description of this algorithm. So we have a supermodular function f on the subinterval, some interval. Then we have to calculate, so rule 1, rule 2, and then we get the solution. And the solution is a subinterval here. That is subinterval of the larger interval here. And there is a special condition. Okay. And the complexity of this algorithm is very good. So it's just a square. It's a polynomial. It's okay. It is not as good as some other algorithm like n log n, but n square is okay for some tasks. It's okay. So there are comparisons, proofs. We'll skip it. So there is in that file the definition of global minimum, local minimum, but well, it's just from the general background to maybe know this. So global minimum means that there is no such variable, and local minimum means that if it is in the local, there's a Haas diagram, hypercube, and so on. I don't think that we should discuss a Haas diagram right now, but maybe next week we will mention this diagrams and maybe look at these diagrams. What does it mean? I mean definition, because we have such a diagram already in our lecture. Okay, there is the way how we can solve it. Okay, but it's not the end of this lecture, because I have another file. There are books, and it's a special book. Wait a minute. Yeah, it's one of a recommended book. I don't remember the name. There, Golden Goring 2012. Here you can check. There is a description. We can check their structure of this book. So we have data correction and introduction and so on. But for us, it is interesting that we have a structure of local and global maxima of sub modular set functions, as we have found that there are such submodular set functions for some logistics problems. So now we can use it. If we prove some theorems here, we can use them in solving of our large problem. Okay. So results, these results received by Cherenin and Khachatурov. But I believe they're Russians, but I'm not sure. Well, it even doesn't matter, Western or not Western, it doesn't matter. So let Z be just a real valued function defined on the power set. It's very similar that for our problem, because we can assign a special weight or a special value for subset. It's important that it's not only for members, so for every city, but for sets, for every subset of cities that were chosen for our offices to build there. Okay, so we have S, we have T there, such that S well, T contains I and I contains S. Yes, and I. So and these brackets means that we use all such sets that are in between of S and T. There. So it's some kind of interval here. But when we talk about sets, interval is not something real valued here, because this is the set, this is the set, this is the set, and this is the set here. So there is an interval, subinterval here. Okay, and the function is called submodular here. It looks like it's different than we have discussed before. So we have discussed another version, but here we see something, another one, but it's not a problem here. Sorry. because it's just another way of reading the same. You can check here, but yeah, there are articles that claims that claim the same, but I use Wikipedia just because it is right here. It is a very direct way, and it is very easy, or it is very easy for you to find this information. That's very, yeah. And you have a condition here. We have discussed it before, and we have equivalent of definition here. And you, as you can see, wow, no. We see here that expression. So it's the same that we have discussed before, but it is rewritten in another form here. Okay. And this theorem, well, this one is just definition of submodular function, and this one is definition too, this one, but it is that expression that we have discussed. Maybe you think what is plus and minus, because it is not obvious how we can subtract or add one set to another set, because we can add what kind of subtraction we use, but it's just abbreviation here for this one. So there is nothing. So this one is this one, and this one, this one. So it's S without K, and this one S with K. Like here. And these definitions are the same. There, I believe there should be a proof here. Wait a minute. Yeah. Okay. And not only that variance, but also I forgot about this. There are also some other variants here and here and this one as well. Okay, and there is Max-Cut problem. Well, Max-Cut problem, it is not something that we have discussed before. Maybe later, maybe next week, because now we have not enough time for discussing for the discussion. But the Max-Cut is very useful for logistics when we try to cut off, for example, epidemics, or maybe we want to cut off electricity for the sake of security, not security, safety. Yeah. So, for example, Max cut off, how we can use. So we have a set with some properties, and we want to divide it and then count these edges there. There is a special problem. We can discuss it later. It is very interesting and a very popular problem, Max-Cut. We just have to, well, I just want to mention that this problem is somehow connected to what we are doing now. Sorry. And the important here, okay, then important here, that it's a submodular here. So the object function here of that problem is submodular. Okay, that one. There is proof. There is a Hasse diagrams. We will discuss Hasse diagrams next week. But right now you can check that every two nodes are different in just one member. So these two, this one has two and this one hasn't, but all others are the same. Here we have 1, 4, and they're connected. And these two also connected because just only one. So we take an empty set, this one, and add elements. Then we add more elements and so on. One, two. I believe that is very connected to muddy children problem. It's very it's logic one. So wait a minute here. Yeah, it is. So 8, 16 variants, and but we will discuss this problem later. So it's a muddy children problem in logic, and if we construct some kind of representation of uncertainties, of alternative words, and so on, it will be exactly their Haas diagram. Well, yeah, exactly Haas diagram there. Okay. But I should spend more time later to describe this problem. It's a very fundamental problem for uncertainties and so on. Well, not fundamental, it's a very famous example. Yes, it's not fundamental, it's a very famous example. And this one is just a generalization of that example because we had only 3 agents, but now we have 4. But anyway, we don't use this uncertainty and logic right now and right here. We just have a Haas diagrams that was constructed as I have explained. So we took all sets, all subsets, and we connect those who has only one member that is in one set, and there is no such member in another set, only one member. So it's very important. And there is a definition for subset, local subset. We have discussed it already during our lecture. Well, we have mentioned this, and there is also the formal definition of this. Yeah, Haas diagrams, chain, yeah, non-increasing, and then we have theorems here. I think that maybe today we don't have enough time to discuss all these theorems in details. Sorry, I can't get okay. As I have told about optimal solution and problem formulation of problem, when we had graph, it was very difficult to write here. For Haas diagrams, it's also not very easy, but we can find one way, one monotone way, when every set is just a subset. Well, is a subset of the right set, and we have non-increasing and non-decreasing examples of functions. Examples of non-decreasing function and decreasing function. Okay. Well, I think that today maybe it's time to stop at this point, and then we can continue next week. So we have, I think that maybe 12:20 is the, or 12:30. Wait a minute, I check. Oh, we have not here. No. It's another course. Okay. Sorry, I can see. I believe that to 12:30 today. I don't remember right now. Okay. well, it doesn't matter so much. We have, well, 10 minutes here. If you have questions, you can ask me. If no, I just continue. And I think that it's a good point not to go further, but to check what we have learned at this lecture. And I will check, I will go through all this material in a very fast way to give you the basic idea what we had here. Yeah, I think at 12:30. Yeah. Okay, we have started from the recording the content of the first lecture, the second lecture, and maybe later I will give the whole picture of all these methods. But we have started from the definition and description of the branch and bound ideas. I think that I have mentioned it already, maybe 5 or more times, and maybe I will mention it 5 times more because it's very basic for our course, branch and bounds, and it's not only about logistics. As you have found out maybe that this approach is applicable for many problems. It was used for chess many years ago. Right now, well, I think that now it can be used in chess and other games as an addition to the neural networks and machine learning techniques. Branch and bounds, it's old, some kind of machine learning technique right now, but of course it's not the key part of this algorithm, because we know that neural networks and other machine learning techniques are very effective for playing chess and other things. But branch and bounds were very impressive technique to check the position on this board, on this field of the chess, which we should compute and which we shouldn't compute. So, for example, we shouldn't compute variance, or we should pay less attention when we say that our opponent they use irrational strategy. So it is impossible to see that he will he will make a lot of mistakes. Maybe we shouldn't use this, but there are many variants. It's not just here. And what we should have to apply a branch and bound algorithm? Well, we have to have an algorithm, or at least an idea, to have partitioning, so like eliminating one edge, eliminating one vertex, because we want to have a small problem there. And we need a strategy not only of branching, but we also should have a special algorithm to have a lower bound, and to have this lower bound very fast, because if we have to spend NP exponential time to get the lower bound, then there is no sense in this, because we can do this without any branch about algorithm. Just by maybe not we can, but well, it's more effective to use special algorithm for bounds. It is very interesting that there are some NP hard problems that cannot be solved using very effective lower bound conditions. It it has a relation with approximability, or yeah, maybe this name. So it means that sometimes if you change something, then your solution can be very close to the proof. It's some kind of continuous property. But for some problems, if you change something, the solution differs very dramatically. And in this case, it's much more difficult to construct lower bound, effective lower bound. Okay, so partition, we have to define, well, we have to choose which strategy we should use. We should depth first or width, breadth first, variance here, and bounds I have discussed, branching function. So maybe I have some kind of probability. So we need ordering for this. So here is this description. You can find it in a file that I have already uploaded. Okay, this is the scheme. So we have such optimization, and we have such approximation, and we can have a partition here, lower bound procedure, and subproblem selection rule here. Sometimes we need upper bounded procedure. We didn't discuss testing procedure. We will discuss it. I think that we can discuss it, or in some cases we will try to discuss it later, because logical implications is very important for many things. And then we came to the traveling salesman problem, and we had we have written down some conditions on this to have a lower bound there. It was very important that this lower bound can be found in very fast. Okay, another thing. And we looked at an example, and we checked step by step how it works. Okay, and then we proceeded to stability and sensitivity analysis. Well, I can't say that we have discussed in all details. We have just skipped several details, but you can read it, and maybe you should read about sensibility and stability analysis here. But I have described the main idea of this, and why it is so important, and why it is worth considering. So there is a name of tolerance, but we can use another names like a robust algorithm, but with some special definition of meanings. And we even have a special theorem here for this condition. So sorry, there is a proof here. Yeah, I use proof, and we had a theorem for tolerances of shortest spanning tree, that we had algorithm of Prim, of Kruskal, and we have discussed this algorithm. They're very fundamental for spanning tree, and there is a theorem how we can check the interval of tolerance there. Okay, as you can see, it is Prim's algorithm is used here, not Kruskal. Okay, then we have mentioned, not discussed, maybe in all details, the example. We got this calculation, and we found that this algorithm can give us the bounds of this sensitivity and tolerance things. And then we came to a bunch of problems like facility location, bank account problem location, bank offices location, and so on. And we found out that these functions are submodular, and we can apply theorems that were proven for such functions. And I think that maybe next time we will pay more attention to these theorems of this submodular function on sets, where sets is just places where we want to put our offices. Yeah. Okay, now it's time to, so it's 12:30, and we have to finish our lecture. So thank you for coming today. I'm waiting for your questions. If you have, thank you for questions that you have asked already. See you next week at the same time, and we will just go on with this lecture and with this course. So, okay, now we should finish. Thank you. See you next week.